Hello everyone and welcome to ML Done. I'm actually quite excited today because this is literally the first live coding video of ML Done that I'm going to put on YouTube. And I decided to have two categories, one with coding from scratch, which is pure numpy, and the other one would be coding in PyTorch. So the one that is from scratch is there to sort of help you guys solidify your theoretical knowledge about machine learning and the mathematical derivations behind it and how to implement them in pure numpy. And the one with PyTorch is obviously for those of you who are good with the theory and you just want a fast performing library that you could just mount your monstrous processes on GPUs and kind of accelerate the performance and the speed. So today we're going to open up our coding session with this simple binary classifier. Yeah, and I've also actually opened up the blog post from ML Done, and you can see the link up there. It's about binary classification from scratch using NumPy. And this is the neural network that we want to implement. As you can see, it's a simple perceptron. Your data x1 is one-dimensional, so pretty much scalars. You have a bias unit that is always equal to 1. You've got two weights that you want to train, and these weights help you to linearly combine your input and the bias unit. And that would be W1x1 plus W0x0, and that would be your Z, which is basically the input to the sigmoidal unit. And then using the sigmoid function, you kind of squash the values of Z between 0 and 1, and that would be the output of your network, or y hat, yeah? And then eventually you will use the binary cross entropy function to measure the performance of your algorithm. And as you can see, the binary cross entropy function is a function of the prediction of your network, which is y hat, and the actual ground truth, which is y. Now, one thing I have to note here, this is not a neural network video. This is not a course on neural networks, so I'm not gonna talk about the details of why we use a binary cross entropy function or how we derive certain mathematical formulas as we go along with the forward pass and the backward pass. So this is going to be mostly focusing on the implementation side of things rather than the theoretical side of that. Yeah. So this is the blog post, and you can also find the code that I'm going to write today on this blog post with some sort of nice explanations regarding the math and certain reasons as to why we do certain things. So if you want this in a written, nice format, you can always go to the blog post of ML Done. I'm going to provide the link in the description and kind of review what you learned today. Okay? So without further ado, I'm quite excited. Let's start the binary classifier. So we need NumPy, right? So I'm going to import NumPy as NP, right? And then we're going to do some nice visualization. So we definitely need matplotlib. So we could say import matplotlib.pyplot as PLT, right? So this would be for the visualization case. And now, when we think about the neural network, you have to always think about the functions that are in place to transform your input to the output. Yeah. So what are those functions? And it's a good practice to actually, isolate those functions through implementing them with in different functions in Python, right? And then during your forward pass, you can just call that function, and that function just does them, the calculations and gives you back the result. And this modular design would also help you better to kind of facilitate the troubleshooting process. Yeah. So the first thing that will happen in our perceptron, if you look at the perceptron over here, This sigmoid function, right? We need a function that could get a value, a parameter, and then apply sigmoid on it, and then pass the output, right? So if you think about a sigmoid, this over here, you can see that on the left side over here, sigmoid of z equals 1 over 1 plus e to the power minus z, right? And they also call this the squasher, right? Because it always, no matter what the range of z is, it always squashes it between 0 and 1. So let's implement this as a separate function. Let me create another cell. So this would be my sigmoid function, yeah? So def, let's call it sigmoid. It's gonna get a parameter, let's call it z. And then what it does is it would return what exactly? 1 over 1 plus numpy exponential minus z. And you can always put the whole thing into brackets just to make sure that that 1 plus e to the power minus c, all of it, is your denominator. So this is basically your sigmoid function, right? And if you look at the diagram, the diagram over here, the next function that you need is, after you compute the sigmoid of z and you get y hat, you want to evaluate the y hat, right? So you need this cross entropy function. If you look at it over here, you've got minus the ground truth multiplied by the log of your prediction, minus 1 minus the ground truth multiplied by the log of 1 minus your prediction. Yes? And you have to notice that these logs are actually natural logs, meaning that the base of these logarithms are the special number e, right? So in order to implement, to take a logarithm, a natural logarithm in Python, you just say numpy.log. It's by default, the base by default is e, right? So let's define this binary cross entropy. So my error function, now define, say, cross entropy. Well, to be more precise, it is binary cross entropy. So it would get your y hat, which is the prediction of your network, and the ground truth, right? So for every prediction that you make, you will send the prediction and the ground truth to this function, and you wanted to implement that mathematical formula. Now, if you noticed, in this mathematical formula, your ground truth, in this sense, because sigmoid is always between 0 and 1, your ground truth could be either 1 or 0. 1 would refer to, say, for example, the positive class, and 0 would be related to, say, the negative class. Yeah? So if you notice, if y is equal to 1, the right-hand side of this formula cancels out. You will just end up with minus log of the prediction. And if your ground truth is 0, the left-hand side term will cancel out, and then you will end up with minus log of 1 minus your prediction, right? So I'm going to implement this as some sort of if-else statement here, if y is 1 and if it's not. So it's simple. So if your ground truth equals 1, you would return, what is the term that you're going to have to return is minus log of your prediction, right? So that would be return minus np log, as I said, that is the logarithm with the natural base, of your prediction, which is y hat, right? Else, or you can say elif y is equal to 0. But I know that I'm not going to pass any y to this function that is different from 0 or 1. So I'm just going to put else, so that I know that that's the case when y is 0. In that case, I'm going to return, so look at here. So if y is 0, the left-hand side will cancel out. That would be minus log of 1 minus prediction, right? So that would be minus np log 1 minus your prediction. Yeah, perfect. Now, so you have the sigmoid, you have the cross entropy. So these functions are done, right? And the second thing you need to worry about is the backward pass, the functionalities that you're going to need during your backward pass. So there are two things you need here. Number one, after you generated your error, you want to update your parameters, right? You want to update your W1 and W0. Those are your learnable parameters. So you need to be able to, number one, take the derivative of your error with respect to your prediction, and then take the derivative of that prediction with respect to z. So that would be the derivative of error with respect to y hat. That's the first step of backpropagation that you need to be able to do. And number two is, so you have this sigmoidal unit. You have to know how to take the derivative of y hat with respect to z. In another word, you need to know how to take the derivative of the output of the sigmoid function with respect to the input of the sigmoid function. Because if you can't do it, you will have been able to take the derivative of the error all the way back to the beginning of your sigmoidal unit. And then you will just take the derivative with respect to those parameters, and using chain rule, you multiply all these derivatives together to get the actual derivative of the error, ultimately with respect to your learnable parameters W0 and W1. So error with respect to y hat multiplied by the gradient of y hat with respect to z, multiplied by the gradient of z with respect to W0 and W1. That's what we're going to do. So the number one mathematical formula that we need to figure out is, what is the derivative of the error with respect to your prediction y hat? So I have this nicely derived in this bit. So if you can see, the d of e with respect to y hat is minus y divided by y hat plus 1 minus y divided by 1 minus y hat. So this is what we're going to implement here. So let's see, let me create another cell. Yeah. Okay. Let's call this function derivative of the cross entropy. Yeah. Right. Again, this function would need y hat and y. Yeah. Now, again, if you notice in this formula, you can consider two cases. If y is equal to 1 and if y is equal to 0. Again, depending on the value of y, one term will survive and the other term will cancel out. So if y is 1, we'll get minus 1 over y hat. Return 1. Let me say that again. Yeah, let me check that again. Yeah. Minus 1 over y hat is what you're going to return. Yeah. Else, meaning that if y is 0, the left hand side will cancel out, and then you'll get 1 over 1 minus y hat. So you return 1 over 1 minus y hat. Yeah. Return. Yeah. Perfect. Right, so that would be the derivative of the cross entropy. Next is the derivative of the sigmoid function. Now, if you look at it here, the derivative of sig of z, or sigmoid of z with respect to z, is nothing but sigmoid of z multiplied by 1 minus sigmoid of z, right? So let's define that. So you can call this derivative sigmoid. Let's say I send the value z, x to it, whatever it is. And then you would return x multiplied by 1 minus x. So remember, this value, this parameter that I'm going to send to this derivative of sigmoid function is going to be actually the actual sigmoid value, because I wanted to just multiply x by 1 minus x. So I'm assuming that x is going to be the actual sigmoid of z, the actual value of the sigmoid, right? Nice. this is good. We derived, not derived, but we actually implemented all the functions we needed. So the next step is to actually generate the data, right? So this is the step when we want to generate our training data. Now, because it's a binary classification problem, what we're going to do is we're going to generate some examples from, again, one-dimensional examples from negative class and positive class. And now, because it's a synthetic data set, I'm just going to consider two Gaussian distributions, and I'm going to sample from them. And deliberately, I'm going to define these Gaussian functions visibly separate from each other, because I want to have a nice separation between the values, because I want them to be linearly separable. And the reason for that is a perceptron can converge. A perceptron can classify the examples for your two classes as long as they are linearly separable. If they are not, the perceptron will fail. You're going to need more layers, not just one layer. And that is the classic XOR problem. The XOR gate actually is not, the examples in the XOR gate are not linearly separable, and there's no way for you to actually classify them into their corresponding classes using just one layer and using just one perceptron. So for that reason, I'm going to make sure that these generated data are actually linearly separable from each other, right? So the way I'm going to do this is, let's consider n equal 500. 500 examples is what we're going to do. Next, I'm going to consider two Gaussians, right? So a Gaussian, I have to define it in Python. A Gaussian has a mean and has a standard deviation, right? So first, I'm going to define these values. Let's say mu and sigma, yeah? And I'm going to say like the mu is 0 and sigma is 1, right? So this is going to be the mu and sigma of the first Gaussian. After I sampled my data, say positive examples from the first Gaussian, I'm going to make sure that the second Gaussian would be, for example, whatever the mean of the first Gaussian is plus 5, plus 10, so that it would be separate enough from it, just to make sure the examples are linearly separable. We're not trying to make this data set difficult, because that's not the goal. We just want to learn how to implement a binary classifier from scratch. Yeah. So let's see, x0. So x0 is gonna hold the positive examples, right? So, or negative example, whatever have you. It's just a simple terminology. You can just choose it the way you want. So numpy has this nice package inside of it called random, and then in random you can choose what type of a distribution you want. So you would say .normal, and then when you do that, it would wait for the parameters of the distribution. So I'm going to pass mu as for the mean of this Gaussian, and standard deviation is going to be your sigma that you've defined already, and then you're going to specify how many would you like. So we want 500. So 500 examples of the positive class. So I'm just going to pass n, right? Perfect. The same story for the examples of the other class. However, np.random.normal. Try not to copy and paste the code, by the way. I know that you've already probably been coding with me step by step, but try to retype the same command again. That would be some sort of an excuse for you to kind of practice it, practice the commands more and more, so that you could just have them just like that whenever you need them, right? So the mu, let's just say mu plus 7, whatever the mu of the first Gaussian is. So the center of that Gaussian would be 7 units to the right or more. And then sigma, so the sigma, let's just make it narrower, because the larger the sigma is, the wider your Gaussian would be. The lower it is, the narrower your Gaussian would be. So I'm just going to say make it smaller, because I want to make them concentrated in one region. The example of the second class. All of this manipulation is just to make sure these examples are linearly separable from the examples of the first class. again, I'm going to pass 500. So I want 500 from the positive class and 500 from the negative class, right? But remember that I want one unified, one data set, right? So I'm going to mix these examples together, right? So I'm just going to say x equals, so x gonna have x0 and x1. So now x is a list. It would have 1,000 examples in it, right? And remember, now you want to have also the ground truth, right? So you know that the first 500 are belonging to, say, the negative class, and the second 500 belong to the positive class. So, and you know 500 and 500 is the number, right? So in order to create the vector of ground truth, you need to generate 500 zeros for x0 and 500 ones for x1, right? So to have different labels for each one of those examples, and the order is the same. So the way you would do that, you can again use, you're gonna again have a list, but you can use numpy's built-in function, zeros like, and I think it's called ones like, yeah. So you're gonna say np dot zeros, I think this is the way to write it, zeros like, and the question is how many? So when I say zeros like, I'm going to get the dimensions from somewhere. When I say x0, it means grab this x0, this list. How many examples do you have there, right? Generate a numpy array full of zeros with this size. So it would generate a numpy array with size 500. The same story, np dot, this time ones like, this time x1. Yeah? Now, let's just run the code. I haven't run it yet from the beginning. So the first cell is right, the second cell is right, third cell is right, and the last cell is right. Perfect. Now, it is good practice to always turn these lists into numpy arrays, because then you can use different functionalities that come with numpy array in a nice package. So the way that you could do that is going to say x equals np.array, and then you're going to pass your list to it. So x is a list. With this command, it becomes a numpy array. And the same story, y equals np.array, y. Yeah? So you can just run it again. Now, if you look at it, if I want to say, see the dimensions, x.shape, I believe is the command. And if I run it, yeah. So x.shape is 2 by 500, right? And y.shape, which is your ground truth, is again 2 by 500, right? Now, the next thing is, you don't want this division in terms of like x being 2 by 500 or y being 2 by 500. You want to reshape this into 1,000 examples and 1,000 labels, right? So you want to reshape this, both your data and your ground truth. So that is when you say x equals np.reshape, right? You're going to pass your x to it, and then the shapes that you want. The shape would be 2 multiplied by 500, right? And so that is exactly what you're going to write. So what you're going to say, x.shape 0, it means grab the first dimension of x. The first dimension is 2, and the second dimension is 500. So you're going to multiply these two. So you're going to say multiply it by the second dimension, which is shape 1, right? Let's just run this. Perfect, it's ran. I'm going to do the same. Y equals, I'm going to just, for the sake of better coding, I'm going to show another way to reshape this. You don't need to necessarily call numpy here, because y is already a numpy array. So you can just say y.reshape, right? So you don't need to pass y again here, because you already called reshape from y, right? So you're just going to pass y.shape 0 multiplied by y.shape 1. You could have again use x. That doesn't really matter because they have equal dimensions. So if you run this, let's just run from the beginning because x has changed its dimension. Right. Now if I say x.shape and y.shape, so both of them would be 1000 values. I'm just going to put them separately. So that is 1000, x has the dimension of 1000, so all is good. Yeah, so it makes sense. Now, we have generated our data, we have defined our functions, and the next thing I would say is it's nice to actually be able to visualize this data before we do anything else about it. So in order to do this, we're going to use the scatter plot of matplotlib, right? And remember that with scatter plot, for every point, you're going to need at least 2 dimensions, the x dimension and the y dimension. But remember that our data is actually one-dimensional here. So we're going to have to pass the y dimension. We're going to pass something. So I'm going to pass zeros, okay? So that all the points will have actually no height, but all of them would be nicely set next each other on our horizontal x-axis with different colors and with different transparency, so that we could see whether they're really the positive and negative classes are whether really linearly separable or not. And again, let me go up. x0 and x1 are the actual values that we've generated from our normal distribution. So we're going to use x0 and x1 as the actual values of our data, and we're going to pass arrays that have all zeros inside, the same size of our examples, just to make sure for every example there is a y value that is equal to 0. Okay? We could put any other value, obviously, doesn't matter, but we have to pass that y value, that the height value for every one of our data points, so that we could use a scatter plot. Otherwise, we're going to get an error that it was expecting 2 arguments, but it just received 1. Okay. Now, we're going to use matplotlib that we've already implemented. So we're going to say plt.scatter, right? Now, we're going to use first. We're going to pass our data. Let's start with the positive example. So x0 contains the values for our first class. The 500 values is inside of that. Now you want to pass the same size of x0, but some value, let's say 0, for the height of the visualization, whether 0, 1, 10, 1000, whatever it is. You want to keep it constant, just so all the points would remain the same height next to each other, right? But again, I would say np dot zeros like would be x0, right? And you can actually define a color. You can define size. Let's call the size. Actually, let's define a variable here, because every point would have a size, right? Let's call it area, right? And let's say, I don't know, 200. And now, the size, you show that with S, and for scatter plots, would be equal to area, which is 200. And then you can actually also define the color. Again, you would use C, which would be for color, and you would pass, let's say, red, okay? And then the last point is alpha, which is the transparency of your data point. Let's put 50, like 0.50. Let's just run this for a sec. Yeah, perfect. It is actually showing our data point, and these are just the positive examples, and you can see that there is some transparency there. And let's do the same, just to avoid wasting too much time on this. I'm gonna just copy this, but you try to, at home, try to do this on your own. I'm gonna put x1 here. Try to write it yourself. let's put color blue, again the same transparency. So if you run it, perfect. And again, just to be a little bit better here, let's call the grid. Perfect. Now nicely separated from each other. So you would like to have a nice separation, nice line that separates these two examples, and you'd like to train your perceptron to learn the weights in such a way that the separation actually happens, right? Remember that if you're not using Jupyter Notebook and you're using some other IDE like say PyCharm or Spider, chances are that you're going to have to also call the function plt.show for it to work. Otherwise it wouldn't show anything. Perfect. So now we see the data, right? Now the next part is to actually build our neural network, meaning that we have to start with the weights. Now if you look at here, our weights in this perceptron, we have just two values, W0 and W1. Each one is a scalar. And we tend to randomly initialize our weights, but remember that we tend to initialize them as a very small value. And the reason is we want Z initially to be very small value. Now if you think about it, again, this is not a neural network course, but I'm just, as a reminder, I'm going to tell you the reason. When you're using a sigmoid function would have a huge derivative when at point 0. Okay, when the input is 0, when you take the derivative of sigmoid with respect to its input, if that input is a very small value close to 0, the derivative or the slope of the tangent line on the sigmoidal unit would be very, very sharp. That slope would be high, right? So by this trick, you make sure that the gradients, as you back propagate them through your network, would stay high and they will not vanish. Yes? So in this particular example, it doesn't really matter, to be honest with you, because, well, it's not a big network anyways. Saturation or gradient, vanishing gradient or exploding gradient are of no concern in this network. But just as general practice, general rule, I want to tell you this. Now, I'm going to randomly initialize W0 and W1. Yeah. So I'm going to use a uniform distribution this time. Again, I'm going to use NumPy's random package, but this time, instead of calling the Gaussian, I'm going to call uniform distribution. Doesn't matter, you can use other distributions as well. For this network, it's easy and it really doesn't matter that much. So I'm going to generate, let's say, to be consistent, let's call this W1 equals mp.random.uniform. Now, when it comes to random number generation, you in a uniform distribution, you need a low and a high range. So you ask Python or you ask NumPy to generate a random value from a uniform distribution in between this and that value, between a low and a high value. So before setting them, I'm going to define this value. Let's say low is equal to 0.1, or better yet, let's say minus. And high is, say, plus 0.01, yeah? And I'm going to pass these two. Low equals, let's define this with capital just to avoid any interference with the actual embedded parameters, arguments of this uniform function. And so low equals low and high equals high. Yeah. And you also need to define the size as to how many, with what sort of a shape would you like to generate this these random samples. And the size is going to be, remember, this whole command will return a NumPy array, but the size, you want it to be just one value, right? And this is how you would put it. 1 comma. This is how you define that. Actually, I don't know whether you actually need that comma or not. Let's just run this first. Oops, an error. Yeah, because high, I meant high, so this T is extra here. Perfect. Now, just out of curiosity, if I look at the shape of W1 and that shape. So shape is 1. This is what we wanted. I think if I eliminate this comma, maybe I get an error. No, no error, still fine. But I don't know, it just visually makes more sense to me to put a comma there. As a hint as to there could be more than one dimension to this. Perfect, so I'm gonna do the same for W0, which is the weight of our bias unit. Again, low, high, the same story. Perfect. And if I just look at the values that have been generated, W0 is a numpy array with just one value, and W1 is again a numpy array with just one value, right? In this case, they are both started as negative values. Perfect. Now, next thing is we're gonna actually start our training. So for every training, you're gonna need in neural networks. You're gonna need to define the number of epochs. Yeah. So I'm gonna put epoch equals to 120. That is what I posted in my blog post. You can put any number, 2,500, whatever. Let's say 200. And you're gonna have to define a learning rate. Now, the learning rate usually starts small, yes? And the reason is because you don't want to jump over the global minimum on your error surface. You want the learning rate to be small enough just to make sure you will be more cautious in stepping on your error surface, just to make sure that you wouldn't keep missing your error space just because your step size is just too huge, right? So eta is actually your step size, okay? So your eta, let's start it with 0.001. And remember that usually we have this idea of updating your eta, your learning rate, as a function of time. So in the beginning, it might start with, say, a very, very small value, but gradually as you train, it could gradually increase. So you will be more and more confident into your step size. Now, I'm gonna wrap the video up, well, at this point, because it's gonna be too much of information. I just want you guys to not get bored. And in the next video, we're gonna actually start the training process. We're gonna create some loops that will go through our training set and basically update the parameters, and it will do the forward pass and backward pass, and with some nice visualizations, you will actually see the decision boundary, the way it changes, and you will see how the error would decrease. We would also visualize that error. But for now, I hope that this has been informative for you, and thank you for watching. I'm going to post the link to the blog post in the description, and feel free to send any question or any concern that you might have regarding the code in the comment section of the video. So on behalf of ML Done, take care of yourselves, and bye.